All right, now we're going to talk about the solubility of alcohols in water. So you guys know this already. Water hydrogen bonds to itself. Water's constantly making hydrogen bonds and breaking hydrogen bonds, doing all kinds of hydrogen bond stuff, right? Alcohols have an OH group. So small alcohols are pretty much infinitely soluble in water. Small alcohols. So like methanol, for example. Ethanol. Methanol, ethanol, propanol, butanol, I think, too, is still soluble in water pretty much infinitely. But as they get larger, they become less soluble. So as you get bigger and bigger, say decanol or, octanol, they become less and less soluble. And if you think about this, it makes sense. Because as you're adding more hydrophilic character, as you're adding more hydrocarbons are not polar. So hydrocarbons are not soluble in water. So if I were to ask you, hey, is octane soluble in water? You would say no, Dr. Betts. Octane is not soluble in water because octane is a hydrocarbon. Hydrocarbons are not polar. Hydrocarbons rely on stuff like van der Waals interaction, London dispersion forces, and all that stuff to interact with other molecules. Water is polar. Water relies on hydrogen bonding. This is not going to work. It's a mismatch. So as you become more hydrocarbon-like, you become less soluble in polar solvents like water. When you're less hydrocarbon-like, you become more soluble in things like water. If you're more polar, you're more soluble, right? So these molecules, these small alcohols, are relatively soluble in water. They're extremely soluble in water because they can hydrogen bond. So let's see an example of that. So here's water. Everybody knows water, delta negative at the oxygen, delta positive at the hydrogens. And another water molecule can come on by and say, how do you do? I'm a water molecule. And hydrogen bond. Everybody in this class, for the most part, would already know that. And everyone's comfortable with that. Well, why can't alcohols do it, right? So an alcohol says, hey, check this out. I have a delta negative oxygen too. And a delta positive hydrogen. So water's like, yep, you do. Let's hang out. Because they have the similar electrical properties. They have delta positive here, delta negative there. Everybody's happy. Hydrogen bond. Makes sense? Perfect sense, right? Now, it should also make sense, I hope, that as this thing becomes larger, say, for example, decane. Let's draw a decane. I believe that's decane. Let me count there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's decane. As this tail gets longer, this tail becomes more and more hydrophobic, more and more nonpolar. Water, although water will still interact here, no problem, because it's still going to hydrogen bond to this area. This whole hydrophobic tail, this hydrocarbon tail, has to go somewhere, and it can't go into water. So this whole thing, water's like, nope, get out of here. Because remember, induction is what's causing the pluses and minuses, right? Induction doesn't work over very many bonds. It works over 3. So once you get past 3 bonds, things tend to stop being delta negative, delta positive. They start going back to their normal base character. So although this OH is hydrogen bonding, no doubt to whatever's around it that can hydrogen bond, this hydrophobic tail is going to prevent it from being soluble in water. Okay, so yes, alcohols, small alcohols, simple little alcohols are soluble in water pretty much infinitely, but as you get larger, I believe it's around 3 or 4, I think it's 4 carbons, not as soluble. They're somewhat soluble. Once you start getting into the pentanols, hexanols, heptanols, octanols, they become less and less and less soluble to the point where they're no longer considered soluble in water. All right, so let's talk about the acidity of alcohols. Now, alcohols are somewhat acidic. Their pK is right around 15 to 16. Their pKs are right around 15 to 16, 17, 18. They're in that range. So let's take a look at just methanol. Let's do a more interesting one. Let's do ethanol. Let's do ethanol. Ethanol's pK, and I have to look it up, is 15.5. So its pK is 15.5. So not real acidic. They're not crazy acidic, but they are acidic. And now phenol. pK of phenol is 10. 10.0. So now the pK of phenol is 10.0, which makes it a whole lot more acidic than ethanol. Well, that's interesting, isn't it? So ethanol is 15.5, but the phenol is 10. That's a lot more acidic, Dr. Betts. Why is that? Well, remember, you always want to analyze the conjugate base, right? Conjugate base of ethanol puts all the negative on one oxygen. It's electronegative, no doubt, but it puts it all on one atom. So it's a concentrated field of electrons. Whereas phenol, and I'm not going to draw them, you go ahead and do this as an exercise yourself. This bad boy can resonate all through this ring. So because it can resonate, that can move this negative charge around onto 3 other carbons in this ring. You go ahead and do that resonance yourself. Prove it to yourself that I'm right. And that, by virtue of the fact that it can move that negative charge onto other atoms, allows it to be more stable. So it's not a concentrated electron field or electron area. It's a unconcentrated electron area. Makes it less desirable to protonate. So that's pretty cool. That's part of how acidity works. Is the resonance is a big deal. So now we looked at primary alcohols. We looked at phenols. What about secondary alcohols? Secondary alcohols are actually a little bit less acidic. pK of a secondary alcohol. Let me look that up real quick. pK of a secondary alcohol is right around 16.5. No, it's about 1 order of magnitude less acidic than primary. So, and that's conjugate base will look something like this. So I think it's pretty clear the reason that's less acidic is because this conjugate base now is getting into close proximity to these atoms. Now, what's going on here is these are atoms, no doubt, but remember, atoms are surrounded by electron clouds. So these things, even though there's protons here, there's no doubt there's protons here. The protons are buried on the inside of the group, and it's the electrons that are on the outside of the group. The electrons here and the electrons here are starting to crowd a little bit onto the electrons here, making this conjugate base a little bit less stable, so it's less inclined to form, making it less acidic. So what about, if that's true, a tertiary alcohol should be much worse. In fact, tertiary alcohols are far less acidic than primary. pK of a tertiary alcohol, look that up for you, is 18. So which is quite a bit less acidic than primary. And the conjugate base of that looks something like that. And now you have this negative charge here being forced to be close to these big groups. Remember, there are clouds of electrons. These cloud of electrons here, cloud of electrons here, and here. So there's 3 big clouds of electrons that are going to be getting in close proximity to this negative charge, which is a big cloud of electrons. It's going to be less inclined to do that. It's going to take more energy to get there, so it's going to be less acidic. Now, what about if we take your ethanol and we put an electronegative atom out here somewhere? Well, the pK of that, let me see if I can find it here, is 14.3. Oops. Chlorine, pK of that. And let's draw the conjugate base. I think everyone will be okay with this because the conjugate base should be now stabilized, right? even though you're adding, a cloud of electrons, right? But the atom you're adding is quite a bit more electronegative. So by induction, the chlorine is pulling electron density away from the carbon atom that it's attached to, making this carbon atom somewhat more electronegative, which will pull density from this carbon, which will pull density from the oxygen, making everything down the cascade a little bit more stable, making this oxygen a little bit less reactive, giving it enough, or decreasing its basicity enough to make it want to form a little more, making the parent alcohol a little bit more acidic. And that's because of the inductive effect. So if you change this to a fluorine, it'll be even more acidic. Okay? And this is kind of how acidity of alcohols is working.